Hey everyone, this is Jon with Radenso, and today Rob and I are going to do what I think is a pretty cool video. We're going to take a look at a bunch of signals that are actually really present in our ambient office environment, and then we're going to run them through various types of DSP, so you can actually see what it looks like before and after to kind of get a visual sense of what your radar detector is actually doing. But before we jump into that, I wanted to take a second to explain that we're going to start using terminology in a way that's true to its actual meaning instead of a generic way that we've started to develop. So what am I talking about? Let's take one example of filtering. What is a filter, right? When we talk about filtering on RD form, we're only using it in a specific way, and it's kind of generic. We're saying, does a radar detector eliminate blind spots? And if we say yes, then it has good filtering. But obviously that's not what Instagram's talking about when you apply a filter to your picture. It's not what Photoshop's doing when you apply like a vintage look or some kind of art filter to your picture. That's a totally different type of filter. And I think it's interesting that on RD form, because we're only looking at a very narrow application, we've started using these terms and kind of developing our own meaning to them. And that can be confusing to people if you jump into this video without having followed along to all the previous context. So when we talk about filters in this video, we are not talking about really anything that is even related to eliminating blind spot monitors. Theia doesn't need to do that because we use artificial intelligence. However, Theia does use tons of different filters before the AI even looks at the signal to eliminate interference, to get better signal to noise ratio, to change the contrast on a signal, so to speak. So we're using filters just like every radio does, but we are not using filtering the way that RD form talks about it. So I did just want to take a second and explain that as part of our educational push, we're going to start using terms in the way that the rest of industries and the rest of academia uses them, as opposed to kind of what RD form does, because we want you guys to understand how these things actually work, what your radar detector does, and how it sees the signal. And I think this video is going to be a good first step to help you guys come along on that journey with us. So I hope you guys enjoy the video. As I said, I think it's a little bit nerdy, but you're going to get to see real signals and real DSP in action. So at least I think that's interesting. Anyway, take care. Hope you enjoy the video, and we'll talk to you soon. Hi everyone, I'm Jon with Radenso.
This is Rob with Radenso.
And today we're here to do DSP Part 2. So last week, if you guys joined us on our channel, you saw us introduce the basic concepts of what is DSP, why is it important for a radar detector, and we had a really positive response. So today, what I think we should do is go one step farther and maybe actually look at a signal, take a look at some analog hardware that DSP replaces, right, and do some visual actual examples of what this stuff does.
Sure.
So I think the first thing to understand is that when we say digital signal processing in the last video, we said that it replaces signal processing applications that analog hardware used to do.
Right.
So can you maybe show us some of that analog hardware and explain like what those would do in a radar detector if we
Sure.
have those here?
Yeah, we have a few pieces here. There's a lot of stuff that still has to be done in analog hardware. Everything before the DSP, before we digitize the signal, is still done using conventional parts, but we get rid of a lot of that at the lower frequencies after we've down converted. So one of the things we're going to talk about today are filters. And I know that the word filter gets thrown around a lot. There's a lot of different kinds of filters that do a lot of different jobs, so maybe we can talk about what filtering is, what it looks like, how it's done, and how it's done in analog versus digital.
Yeah.
We're also going to talk about what a mixer is and how we are doing some mixing in DSP versus analog and what the two differences there might look like. And we might also talk about power measurement, what it is typically used for in a radar detector, and what we're doing with it digitally to do our power measurements.
So is it correct of me to say, as somebody who's not an engineer, that these basic signal processing applications, whether they're done in analog or digital, things like filtering, mixing, power detection, are these kind of like the building blocks of a radar detector at a fundamental level?
They're the basic building blocks of any radio system, transmitter, receiver.
So even like your FM radio?
You bet. These are pretty much ubiquitous. They're in all sorts of RF electronics, and at the end of the day, our radar detector is just another radio receiver.
Interesting. So these all developed then because before the processing power and the technique was there to do it digitally, this is just kind of like the origins of radio? These kind of things?
They're basic RF electronics. So in our application, we are able to use digital analogs of these basically, right? We can replace a lot of this stuff with the digital equivalents, but these still have an amazing amount of use in other systems. We're just fortunate enough to be able to replace a little bit with our digital equivalents.
So this guy right here, this is labeled low-pass filter. And before we talk specifically about low-pass filter, what's the point of a filter in general? I mean, is it the same kind of thing like when you're filtering coffee where you want to get rid of the stuff you don't care about and only let through what you do care about?
Right. It can be a subtractive process like that. A filter is, in our use of the word filter, there's a whole bunch of different kinds of filtering. But when we talk about filtering, we're talking about a system that either enhances or reduces part of a signal. So when we are talking in the terms of low pass, high pass, we're talking about the parts of the spectrum that we're going to reduce or enhance. So we're going to, when we say a low pass filter, for example, we want to pass low frequencies but not high frequencies, just like in a coffee filter.
So an easy way to remember it, low pass means you want to let low pass.
Right.
Literally, that's what it means.
You bet.
And I assume the same is for high pass?
Correct. And then band
pass,
and we'll talk about that as well.
Now, before we actually get into looking at the signals, one question I had is these are huge. So obviously there's miniature versions of these that for radar detectors would be built into the front end, right? They're not actually, like this is a laboratory one that's designed to be easy to interface with. So like radar detectors, they would have things that perform the exact same function. You could build a low-pass filter into an analog radar detector. It would just be smaller.
Well,
I just don't want people to get confused about how
well, not
giant
necessarily.
that is.
You build a filter based on exactly how it has to act, and sometimes a filter has to be that big to achieve the things you want it to achieve as far as its frequency specification, the amount of power it can handle.
Okay.
So there's a lot of parameters when you choose a filter. So you can get pretty close with very, very small parts like you might see in a detector, but getting very, very close without a lot of parts and a lot of expensive parts is really where DSP shines.
Interesting. And I guess that's, if they do have to be larger, even if they're not quite that size, I guess that's kind of why, just from a mechanical standpoint, why you're limited to only looking at things one or two ways with analog, because there's not enough space in a radar detector.
Parts take up a lot of space.
If you want to build 10 different filters that you can select from, your radar detector would be that big then.
Right, and you see a lot of, I mean, there's a lot of very, very big devices to do stuff that is done much easier in digital for different reasons, but when you look at, you know, some gigantic base station for a cell tower, a huge amount of that size is filters.
Really? I actually didn't know that.
Yeah.
That's interesting. So, all right, so let's maybe, in a radar detector, why is a filter important? Does that get you better range, or does it help you filter out BSMs?
Well, it lets you do a lot of things. It depends on what you're trying to do with the signal. For us, if we have a signal that we want to evaluate to say, is this a police radar or is this Wi-Fi, right? We want to filter out signals that we don't care about so we never have to worry about evaluating them. So one of the things we're doing is using these filters to reduce components that are coming into our signal from being mixed in the horn, or from Wi-Fi that's all over the place, or powerful interferers like FM radio stations. You don't care about any of that because none of that's a radar gun.
When all that stuff does come in that you don't want, that could possibly mean less sensitivity for what you do want, right?
Right. What we want to do is make sure that the signal that we're representing, that we sample, consists of just the frequencies we care about. We want to filter out frequencies we don't care about and remove them from the background noise, and we want to make sure that what we digitize is a high signal-noise ratio representation of signals that we actually care about.
Okay, so like that's one example of where a filter would be in a radar detector, is literally right after the horn then.
Correct. We do have we have filters in and after the horn. We want to reduce the signals that come into the horn that we don't care about, that are down converted to our intermediate frequency, so we filter those out. And then we want to filter out frequencies on the digitizer board that might be received accidentally from, you know, other
filters aren't
emitters.
perfect.
They aren't perfect.
Especially analog filters. So that's one thing to keep in mind. And one of the reasons DSP is so powerful is because it helps you make more sense of what might accidentally be the unwanted signal that slipped past your analog filter in the front end.
Right.
Interesting. So filters are a fundamental building block of radar detectors then,
Right.
or really pretty much all DSP.
All electronics, yeah.
What about the mixer? What is that? Because I was actually confused about what this mixer was when I heard the name. I thought it was just something that just like combined a bunch of RF stuff.
Well, it kind of does. Mixers are a little bit harder to explain
Easily,
as succinctly as filters, and even that explanation of filters doesn't do them any justice, right?
But we're trying to keep things
right.
Eli 5 here.
Sure. What we use mixers for specifically is to convert a signal from one frequency to a signal of another frequency. Our horn is built to receive very specific frequencies in X, K, and Ka band, right? But we don't want to process them there. We want to convert them down to a lower frequency where we can then digitize them and start doing DSP.
So you can actually mix frequencies. Let's say that we have our Ka band that comes in, it mixes with the output of our local oscillator. So now we've got a nice 1 gigahertz signal that has all the information. Once that's digitized, we can mix that again?
We can.
Digitally?
Right. And
why would we want to do that?
Well, we're going to mix down. When we use our mixer, say we want to turn 34.5 gigahertz down to 1 gigahertz for sampling and digitizing, well, we're going to convert down a tremendous amount of bandwidth. We don't want to look at all of that bandwidth. We want to look at a small amount that we can feed to our analog to digital converter so we can start doing DSP. We would typically use, or I think that it's almost every detector now would typically use a second mixer, right?
An analog second mixer, yeah.
Correct. To then turn the bulk of what we down converted and finally tune it for a second down conversion to a second IF. So what we would typically use another mixer for is to fine tune the down conversion process to another lower frequency that would be good for our digitizers to sample.
So I guess I'm confused though. How are we mixing that digitally if it hasn't been sampled yet or digitized?
Well, what we're doing is we're sampling this. We are doing that. We are mixing it, but then we do sample it. And once it's sampled, instead of we now have a lot of latitude once it's digitally sampled to digitally mix it,
okay,
and to move that digital representation up and down in frequency.
Okay.
So we sample it, but then we use digital mixers internally to fine tune our IF once it's been sampled and to frequency shift our IF.
Interesting.
Yeah.
And then you said we have another component here, a power detector.
Yeah, we have power detectors, and these are all over the place in electronics.
So what's a power detector? Is it just what it sounds like?
It's like what the Spectre is, right? When you look at a radar detector, that's essentially a horn with a power detector on the back of it. It looks for a very specific signal and detects the amount of power that is in that signal. And that's what sets off the alarm. When we were working with the radar detector, we could see that green LED that was connected to its power detector. In the Valentine, there's a logarithmic power detector behind the DDL. There's power detectors all over the place to measure the amount of energy that's present in a signal. And
so it almost sounds like that's a radar detector.
Essentially, that's
in a lot of ways.
Right.
I mean, if you're sensing that there's power present in K band.
And that's the biggest problem with BSM filtering is that with a conventional radar detector, you're essentially using a very sensitive front end and very sensitive receiver and detecting the amount of power that's present. And that's hugely problematic because there's BSMs put out power, garage door or grocery door openers put out power, and police radar guns put out power. Power is a quantity that we measure all the time for different reasons. Even in Theia, we do so digitally, and we don't necessarily rely on power detection for the same purposes, right? So one of the things that we do digitally all over the place is power detection, logarithmic power detection to drive our automatic gain control, but we do it all in the digital domain by looking at the power contained in the samples instead of the power contained in the analog signal that's coming into the radar detector.
Interesting. So maybe to get a better understanding of filters, since I think they're probably the easiest to understand, do you think we could take a look at some real signals and then maybe run them through a filter to show A and B?
I think we can do that.
Okay,
yeah.
Cool. So this screen right here has a ton of stuff on it. what we've done is we've set it up so that we have a signal of interest, and we actually generated a modular threat to make it hard. This is kind of similar to like what a red flex camera would look like. And Rob, can you point to that, the signal of interest?
Yeah, this is our signal of interest, and this is just a linear CW sweep that we put together. And this is kind of like a little bit of a slower, narrower band version of what you'd see in a BSM or a red flex or something like that.
Yeah, or even like a gatsometer. I mean, it's not exact, but this is pretty much what it would look like.
Right, same principle.
Now, I also see a whole bunch of other energy present here. That's all just stuff that we don't care about. It's interference because this signal is not really filtered right now. This is just what the ambient environment, this is what our world is like
around
us.
I just randomly chose a frequency here. I think this is around the LTE cellular band.
And this is real, this is live, this is
right,
actually
there's the antenna right there next to you.
This is what our spectrum looks like.
Right.
I mean, if you can't see all this, but it's everywhere around you. It's really crazy.
Right, and this is not far away from the frequency that our intermediate frequency resides at inside of Theia. So these are signals, maybe not these ones specifically, but signals just like this are things that we have to be cognizant of and have the ability to filter out.
So if we didn't have any filters, and this is what your radar detector was looking at, what are some of the downsides, Rob? Would you see less sensitivity, or would you see more false alerts? What would the consumer see for a signal that just wasn't filtered?
Well, first of all, it really depends what you're looking for in the signal. If you want to look at power, with our signal on or off, there's still a tremendous amount of power in this spectrum. If we're looking for modulated threads, there's a bunch of really widely modulated signals in this spectrum. If you're looking at the FFT of this to try to measure where there's energy all over the place. It makes it very hard to distinguish a signal of interest from other signals that happen to be interfering.
Which doesn't make a really good radar detector.
Right.
I mean, that's the opposite of what we want.
Sure. So basically, being able to filter and helps us look for a known quantity or helps us evaluate a quantity without having to also evaluate signals that are present that we don't really care about.
Okay. So can you hand me the low-pass filter over there?
Sure.
So this is the low-pass filter. I'm not saying this is an ideal strategy to use here, but can we just see what it looks like, just so we can intuitively, visually understand what a low-pass filter is?
Okay, but before we talk, let's one more time go over what we're going to be doing here.
Okay.
When you look at this spectrum, right, we're looking at about 25 megahertz of bandwidth.
And frequency is left to right on this screen,
right? So we're looking from here to here is about 25 megahertz of difference. We have a few filters that we've built in DSP, and these are pretty equivalent to an analog filter. We have a low-pass filter, and what we anticipate that doing is letting these low frequencies pass, but not letting the high frequencies pass. So we have frequencies going from low to high.
So for us, that's actually going to filter out our signal of interest.
Correct.
Because it's a higher frequency signal, and our low-pass filter is only allowing low frequencies through.
Right, and what else? Another thing to keep in mind is that we're going to switch the way this filter works by basically reloading it and telling it what kind of filter it is, but it's the same filter. So we have a filter we're going to run here that is running in DSP, and we're not switching out filters, we're just reprogramming this filter to do a different job. So the first job we're going to do is a low pass. So let's see, low pass. So you can kind of see,
That really knocks it out.
It does, and it's one of the great things about DSP is that the sharpness of a filter is only really limited by the computational resources you have. The FPGA that we're using happens to be remarkably good at doing this kind of work very efficiently and very quickly. So you can see that with a low pass filter, the low frequencies pass and the high frequencies are attenuated or stopped. Unfortunately for us, this isn't doing us much good because
what we care about seeing, we just filtered it out. So
and that's unfortunate with analog hardware. You don't get the ability to tell a low pass filter that it's now a high pass filter.
So this is important too, because when stuff like MRCD and MRCT came out, people said, on the older detectors, for example, I'm not talking about the newer digital detectors. If you have an old analog detector and a new threat comes out with a different type of signal, you're kind of screwed because you soldered a bunch of these into your circuit board, and you can't just say, "Oh, I'm gonna bypass that." You'd have to do new hardware.
Right.
But if you don't do it in analog and you do it digitally, you can do what we're about to do right here, which is just literally press a button and reprogram your filters.
Correct.
And it doesn't cost you any resources hardware-wise.
Right. Once you have the filter, That's the resources. And now you get to have that filter behave any way you want to without affecting the amount of resources it takes.
So, all right, so we eliminated our signal. Let's try a different strategy. Maybe we should just let all the high frequencies through.
Right, we knew that the frequency of interest was a higher side frequency, so instead of doing a low pass, let's do a high pass.
Okay.
So this is a low pass, and here we go. There's a high pass filter.
Okay.
The low frequencies are stopped, and the high frequencies pass.
So this is better because we can see our signal now, whereas before with a low pass we can't. And we also managed to get rid of about half of the kind of like noise or BS that we don't want to see in our signal.
Right.
So this is better. We would still probably get better range with it, but there's still a lot of junk there.
Well, think about what happens if you take a low pass filter and then you put a high pass filter after it, where you are only passing one specific range of frequencies that falls between that low and high pass. That's called a band pass filter. And
so just to clarify, because I'm a little slow sometimes, so a bandpass filter is basically two filters that you can widen or narrow and hone in on exactly what you want, and it only lets through what you care about.
Correct. So the next filter we have is a band pass filter, which is kind of a combination of a low and a high pass. We want to put the low pass frequency here so that all these frequencies pass the low pass. We want to put the high pass here so only frequencies beyond here pass, and when those two come together, we're going to have a band pass filter. And that's the last one we have here.
Wow. So if I'm a radar detector right now trying to pick up this particular signal, that's a no-brainer.
Right.
I don't even see garbage radar or Wi-Fi or anything else. It makes it super easy for whatever's controlling your radar detector, whether it's AI or just a traditional microprocessor, to say, oh, I recognize that. That's exactly what I want to go after.
And this is what we do a lot of what we're doing in the DSP is basically conditioning this signal to make the most sense for the neural network and the AI. So a lot of what we're doing with the DSP and a lot of what we're doing with the resources on the FPGA is DSP to basically enhance parts of the signal or remove parts of the signal to make it easier for the AI to correctly inference on and give us a good detection with no false alerts.
So given the fact that we're doing this digitally, if we wanted to, right now, you could actually go back and look at the original unfiltered signal because it's just the samples, right?
Sure, yeah.
So does that allow us to get really complex and creative strategies where we can kind of have a bird's eye view of the whole thing and then selectively at will say, I want to look here, 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 give me a bandpass filter here.
Sure.
Do this, increase sensitivity here, I don't want to see this. And can we do all of those things at once because we have an FPGA?
Yeah, it's great. We can superimpose a lot of different DSP algorithms on top of one another. And as opposed to something like a microcontroller or a CPU, where you are doing these things serially, you execute one instruction and then the next and then the next. We can have all these things happen at once, and they've already used the resources they're going to use by existing on this FPGA that we've built. So we can do any number of operations to the same set of samples, switch them on or off, arbitrarily, and affect how they work in real time arbitrarily.
So I don't want to go too deep into this just because I don't want to make this video a hardware video.
Right.
But like, when you say a microprocessor, I know that a lot of popular detectors, and some very good ones, like the Uniden R3 and R7, use Blackfin DSP processors. So is that an example of something that is really, really good at something, but it can only do it like linearly, one at a time?
Well, it's really, really good at a lot of things when you're talking about a Blackfin. It's really, really good in a lot of ways that I definitely wish we had in the FPGA, which are some of the peripherals, right? It's really easy to program. Anybody who knows kind of basic C programming can use those development tools to program a Blackfin to do a couple of these operations.
So like a Blackfin can do a bandpass filter, no
right,
problem.
But that's the thing is with an instruction-based system, you are doing these instructions one at a time. You have these resources that can perform an instruction on some data. But with us having the latitude to basically build the chip however we want it by programming it, we don't have those same constraints. So we can have all of our different DSP operations happening in true parallel, completely concurrently. We are not in a way where we have to share basically timeshare one resource for all these operations and have everybody waiting in line to use it.
So by virtue of the FPGA being parallel and being able to really run multiple DSP operations simultaneously, just continuously going, like it's almost like slices, right?
Right, right.
If you have like a slice for a power detector, a slice for a bandpass filtering or whatever it is, a slice for mixing, all of those could continuously be performing that operation in real time.
Right, and you've probably heard the term pipelining, right? You have a pipeline where a sample has one thing happen to it and then another and another, but at the same time this pipeline has all the samples. So as your first sample is going through its second operation, the next sample is going through its first, and so every sample as they pass through goes through one DSP after another.
So in a way, by virtue of being able to run digital signal processing in parallel, is it accurate to say that we can almost have several specialized mini radar detectors for different types of threats within our actual radar detector?
Yeah.
So like if we're trying to detect MRCT or draw a pretty picture for Ray, our AI, of what MRCT looks like, in the FPGA, can you have a DSP slice specifically optimized only for a modulated threat like MRCT?
Well, you can, but...
And then could you have another one that's more specialized towards CW enhancement?
Well, what's really great is that, you know, with us being able to reload these filters and have them do different... If we have one very, very complex filter that can have very, very complex functions assigned to it, you can basically describe how to reload it for all those tasks and have one filter that can do all those things. But yeah, absolutely. We're running several filters at this point that are in different stages of the processing chain, but you can either have one filter that you can tell, okay, you're specifically here to filter out a BSM, or you're specifically here to
so like you
enhance an
could
MRCD.
create like an Acura filter, and it could just always be running.
Right,
Yeah.
and we'll talk about match filters in another video, but we can talk about what a filter bank and a match filter looks like.
Yeah.
And, but absolutely, yeah, it's really great. A lot of our architecture gives us the freedom to choose whether or not we want to put in more filters or just make one that we use for everything that's very, very sensitive.
Yeah. Interesting. Well, that's fascinating, and it's amazing to be able to see the difference. Like if I'm a radar detector looking for that signal, I mean, yeah, that's a no-brainer.
I mean, we're using a mouse wheel to set these coefficients. In our product, we can basically change these tens of thousands of times a second and basically say, you know, for all these different filter profiles, look at the different responses to help us understand how to better elaborate some signal features for the AI.
Cool. Awesome. Well, I hope you guys can understand some of the basic concepts of DSP, the building blocks of DSP, like filtering now. As Rob said, we want to start doing this a little bit more often in the future, and we'll get into some more advanced concepts later. But I really love this stuff. I love learning about it. I don't know that much about it, frankly, so it's always fun for me to kind of sit with Rob and ask what he's doing, and I'm hoping that it's similarly interesting to you guys. So I guess until next week, everybody stay safe, don't get tickets, and don't forget to subscribe and like to our YouTube channel if you haven't already for a lot more Theia and just educational content going forward. Everything we talk about here is not specifically for Theia, not even specifically for Radenso.
Right.
This stuff is how your Max 360, your R7 works, your cell phone.
Right, when you hear the word DSP.
These are radio concepts.
Yeah, when you hear the word DSP, I'd like you to know what it means.
Yeah, exactly. It's not a buzzword. This is something that makes all of our lives better every single day.
You bet.
So, cool. Take care, everyone.
Thanks for watching.